The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thanks for joining us for another webinar in our continuing AMS webinar series. Today's webinar, the topic of today's webinar is Introduction to 2.5-axis Machining or Milling. My name is Joe Anand, and I'm the product manager here at MecSoft. As usual, I'll be joined today by Uday Honalagore, our support manager, who will be actually doing the demo. Before we get started, I would like to mention that this webinar is actually the first one in a series of webinars that will be part of a set of instructional resources that we are compiling for our CAM products. We will make this set available to all AMS customers for reference once we think we have a complete set ready. So stay tuned for that. Before we actually get started on today's webinar, a few housekeeping tips. Recording of this webinar will be made available to all registrants in a day or so. It'll give us some time to clean it up, and then we'll post it. It'll be a YouTube video link that we'll send to all our AMS customers who are registered for this webinar. And also, we would like to keep this webinar as interactive as possible. So we would welcome your questions. If you have any questions on what were they showing in the demo or any general questions on the topic, please go ahead and post it on the chat window that is shown in the graphic on the GoToWebinar panel on the right side with the big red arrow pointing towards it. I'll be in the background monitoring the questions as they come in and answering them, and so feel free to be as communicative as possible. We also typically reserve the last 10 minutes for questions if time permits and also if it's necessary. But please don't wait for the last 10 minutes. You can keep typing those questions in, and we'll be answering them as quickly as we can. Next slide, Uday. So today's topic, as I mentioned, is Introduction to 2.5-axis Machining or Milling. And the topics that we are going to be covering, are we going to be starting out? This is going to be a very introductory type of webinar, so we're going to take it slow and then walk very slowly through all the different terminology first, starting with what is 2 and 2.5-axis. And then we'll talk about how you actually do part orientation and setup and get ready for milling, the actual machining workflow. And then we'll go into the 4 machining methods that we have going to be showing today, which is face machining, pocket machining, profile machining, and then finally engraving. And then once we get all the machining done, we'll also be showing how to post-process the internal toolpaths out to your favorite machine tool controller. So next slide, please. Yeah, now we're at the demo portion of the webinar. So Uday, it's all yours.
Thank you, Joe. Hello, everyone. Good morning, good afternoon, or good evening, folks. And thank you again for joining us today for our AMS webinar series. Today, we will be covering Introduction to 2.5-axis Milling. And we'll be covering this in both RhinoCAM as well as in our standalone product, VisualCADCAM. So first, what we're going to be learning about is what is 2-axis or 2.5-axis? What does that terminology mean, and how is it different from the other type of machining methods like 3-axis? So 2-axis or 2.5-axis is typically used with machining or programming of prismatic parts, where there are no negative drafts or draft tapers or drafts, positive drafts, and it's like a straight extrusion with either a planar floor or through a hole like what you see here, and there's no sculpted surfaces and no sculpted surfaces geometries in here. So consider like you have a bunch of curves or sketches with a straight extrusion. Those parts can be programmed using 2-axis or 2.5-axis. So in the case of 2-axis or 2.5-axis, your tool or the cutter maintains a constant Z as you're moving in X and Y. So that's why it's called 2-axis, where the X and Y keeps moving and your Z remains at a constant depth. The way it's called 2.5 axis is because you can step the Z into multiple levels. So let's say, for example, you have a part that's about 3/4 of an inch in thickness, and you would like to mill the part in multiple steps. You could go in steps of, let's say, 1/4 inch per cut. So that's where the 2.5 axis comes into play, where the Z remains constant at a particular depth as you're cutting in X and Y, and then you're stepping it down to the next level to remove material. So it's called 2-axis or 2.5 axis milling. As the cutter moves in X and Y, the Z is maintained at a constant depth. And this can be done automatically in the program, so you don't have to step at each level. You specify like a total depth and your depth per cut, and this, RhinoCAM and VisualCAM will take care of that, handling that for you in multiple depths per cut. And we will be covering that during today's webinar. So that's basically what it means is 2-axis or 2.5 axis machining. Now, what I have here is a prismatic part. As I talked about, prismatic part is basically a part which does not have any sculpted surfaces, no drafts on it. So a simple straight extrusion of a bunch of curves or sketches that you may have modeled. To program 2-axis or 2.5 axis operations, we could work with solid geometries, surface geometries, mesh geometries, which could be like STL files. So any of these 3 types of solid surface or mesh geometries. We could also program 2-axis and 2.5 axis by just using 2D geometries like wireframe, like curves or sketches. So you could be importing in a bunch of curves or wireframe geometries in the form of DXF or DWG, or you could be even creating them or drawing them in the CAD here. So in today's webinar, we'll be focusing on how we can program 2-axis or 2.5 axis using a solid geometry in here. So the part what I have loaded here, as you can see, is a prismatic part. You can view it from all 4 views: top view, perspective, front, and right side view. So the first thing we want to do here is we want to make sure the part is being oriented correctly for machining. So when I say oriented, you want to make sure that the part is oriented to fit your work envelope of your machine tool. So typically on a mill, you have more travel on the X-axis compared to the Y. If you're working in a router, you may have more travel on the Y compared to the X-axis. So if you need to orient the part or reorient the part from the way it's imported or modeled, you need to rotate it. So there are several ways how you can orient the part or rotate the part. One is using the tools that are available in your CAD system. So since we are working here in Rhino, we could take advantage of the tools in Rhino. I can select the part, and I can either use the gumball to rotate the part. I can say I want to rotate it by 90 degrees to reorient the part. So now you can see that the length of the part is oriented along the X-axis. So you can use the tool that are built in your CAD system, or you can use the Orient part feature that's available in your CAM, in RhinoCAM, by going into your Program tab under the Mill browser, and then under the group called Setup, you'll find Orient part. You can select Orient part, and in this particular step, we want to orient the part so that the part is rotated about the Z by -90 degrees or 270 degrees. So I can specify a spin angle in here to rotate it. I'll put in -90, and then I'm going to rotate it about Z axis. So you'll notice that the coordinate system is now being transformed in the preview, and then when you click OK, it orients the part to line up with the world X-axis, world Y, and the Z axis. So I'm going to pick OK, and you'll now notice that the part is rotated. So for those who are not very familiar with the coordinate system, so the red arrow represents the X-axis, the green represents the Y, and the blue represents the Z-axis. So this is what we call our triad, which represents the X, Y, Z axis, and it's lined up with Rhino's coordinate system. So to orient the part, you could either use the CAD tools that are built into Rhino, or you can use the setup orient part feature that's available in RhinoCAM. So there's multiple ways of doing it. Now, let's go ahead and position the part so the lower left corner of this part is at the origin. So I'm going to line it up. So to do that, I'm going to use align, set world coordinates. I'll pick set to part, lower Z, southwest. So I'm just going to position the part so that the bottom left corner of the part is at the origin. So you'll notice that in the perspective view or the isometric view, the XYZ origin is at the lower left corner and the bottom of the part material. So the part is now oriented and is now ready for our programming. So we talked about orienting the part. The next step is the setup. The setup basically is the XYZ orientation, the coordinate system. Now, by default, in both RhinoCAM and VisualCADCAM, the setup is automatically aligned to the world coordinate system orientation. So, which means your top view, if you're looking down from the top view, your x-axis goes from left to right, the y goes from front to back, and the z is pointing towards you. So the coordinate system orientation is in the same orientation as the world coordinate system in the CAD system here. Now, as I've mentioned here, the red arrow represents your x, the green represents the y, and the blue arrow represents the z-axis. So when we program a toolpath, so this would be your x-axis, y, and then the z-axis motions. In the next step, we're going to define the machine tool, and then we'll select the post processor. So that would be our typical workflow. So we would go into the program tab, and we work our way as we work through these groups, working our way from left to right. So we would want to define the machine tool. So select machine. For both 2 and 3 axis operations, the number of axes will be set to 3. For multi-axis operations, we have options for 4 and 5 axis. Today's webinar will be focusing on 2 axis, so we'll set the number of axes to 3 axis. The next step is to select the post processor. Now this could be done either towards the end when you're ready to post process the code, or at the very beginning where you can select your current post processor from the list of posts that are included in RhinoCAM, or you could even edit to build your own custom post processor. For our webinar today, I'll just go ahead and select a FANUC post processor. The posted file extension, you could set it to .nc or whatever is the preferred extension for your machine. If the extension that you're looking for is not found in the list, you can choose add new to add a new extension to the list. So we'll pick .nc. So we oriented the part, we established a setup. In the next step, we're going to go ahead and define our stock geometry, the stock material that you're going to be using to mill this part. So we'll pick stock and we'll select box stock. So the box stock allows you to establish or specify the length, width, and the height of the stock material. So if you have a pre-cut stock material of a certain size, certain dimension, you can input those. Length is the distance on the x-axis, the width is along the y, and the height is the material thickness. So I could enter it as a fraction, or I can enter it in decimals. Length, width, and the height establishes the stock. And the stock is now created, and you can toggle the visibility of the stock by selecting stock visibility in the program tab. You will also notice that once you select your machine, post, and stock, all of these information is updated under machining job in the browser. Now, we also have an option to define the stock as a part box stock. If you want the stock to be just oversized around the part by a few thousandths or by a certain offset distance, you can specify it as a part box stock, or you can specify the offset in the X. I could say the stock is offset by 100 thousandths in the X, 200 thousandths in the Y. And in the Z, I can specify its offset by 50 thousandths. And I can choose whether the Z offset is going to be the positive Z only, negative Z only, or you can do it in both positive Z and negative Z directions. So you can specify offsets using part bounding box dot. Now for our purposes today, we'll just stick with the box dot where we input the dimensions, the length, width, and the height, 3/4 of an inch. Now, once the stock is defined, we would like to go ahead and align the stock to the part. So to do that, we'll select Align and choose Align Stock. And in this process, we're going to be aligning the stock in the Z as well as in X and Y. Now, since the stock that we've defined is slightly thicker than the part itself, we would like to align the stock so that the bottom of the part is flush with the bottom of the stock and there's some material on the top that can be removed. So I'm going to use Z alignment to bottom. So you'll notice that there's some material being left on the top, which we can use a 2-axis machining operation to remove that material. We'll be talking about that in a few minutes. And then we would like to align it in X and Y. So I'm going to have it centered in X and Y. So there's material being left around all the sides, which can be milled out as well. You could also align it in different ways. If you want to have it flush to the side, you can do Midwest or Southwest. Southwest will flush it to the lower left corner. You can do South, Southeast. So you have different options in here. So we're going to pick center, so there's not going to be any factory edge being left from the stock as the part gets milled out. So Z alignment, we're picking bottom, XY alignment to the center. We'll pick OK to accept it. The stock is now aligned to the part. Now you'll notice that the transparency of the stock model when you're in the Program tab is not opaque. And when you go to the Simulate tab, the transparency is opaque. So you can control these transparencies under Preferences or stock simulation preferences. You can control the transparencies of how you want the stock to appear. Now, once you have the stock created and defined, the next step is to specify the location of your work origin, or also known as work 0 or the program 0. Where would you like to establish your XYZ origin before you start milling the part? As you place this piece of material on your machine table, you typically want to pick one of the corners of the stock and either pick the highest Z or the lowest Z to establish your XYZ0. It's called program 0, your work 0, or part coordinate origin. So we're going to establish that. There's a couple of ways to do it. One of the ways to do it is using align set world coordinate system. In this particular step, we will be aligning the origin to the extent of the stock box. As the stock box is slightly larger than the part, you can see the difference here, stock box versus the part box. So the part extent is slightly smaller than the stock extent. So we want to put it to the corner of the stock box. So we'll pick set to stock box. And then for the 0 face, the Z0, I'm going to pick the highest Z, which is going to be the top face of the stock. And for the 0 position, which is the XY position, I'll pick the lower left, which is the southwest corner. So you'll notice that the machining coordinate system origin is being displayed on the top face of the stock and the southwest corner. Now when I select OK, this transforms the part and the stock to the world coordinate system origin. So the machine coordinate system origin and the world coordinate system origin will be coincident. So when I click OK, so this automatically transforms the part and the stock to 0, 0, 0, or the world coordinate system origin in Rhino. So if you go to the Simulate tab, you'll notice that the stock origin is also at XYZ0. It's the top of the stock and the southwest corner. Now this is one of the ways how you can establish your XYZ origin for machining. Now there's two triads that you can toggle the visibility on and off. We have the world coordinate system visibility and the machining coordinate system visibility. So as you click on this, it displays the coordinate system visibility for the world. And you'll notice that the machining coordinate system visibility triad is slightly larger than the world coordinate system visibility. Now, if you prefer not to move the part or the stock, but would like to move the location of the coordinate system origin for machining, you could do that by using work 0 instead of using set world coordinate system. So if you pick work 0, you can choose to move the machining coordinate system origin independent of the world coordinate system origin. So this can be done using work 0. You can choose set to stock box. In this example, I'm going to show if you choose to put the origin to the northwest corner top of the stock, you can say set to stock, ISD northwest, and generate. You'll now notice that the machining coordinate system origin is shifted to the northwest corner top of the stock, but the world coordinate system origin stays over here. So work 0 is one of the ways of how you can establish your coordinate system origin for machining. Now, if you'd like to leave the work 0 at the same location where the world coordinate system origin is, you can edit the work 0, double click on it, pick set to stock, ISZ southwest, and generate it. If you'd like to specify your work offset register number, you could be using like a G54 or G55. You can specify that right in here, your work offset register number, and this will be output in your posted code. Now that we've prepared the part for machining, the next step is to program our toolpaths. So as you go under 2-axis, there are several different methods offered in our 2-axis machining methods. Today we'll be focusing on facing, pocketing, profiling, and engraving. Now these methods are available in all configurations of our mill module. Now let's take a look at facing. What is facing operation? A facing operation is like an area clear operation where you can use to remove material from the top face of the part. In this particular example, we have a stock that's much thicker than the part by a few thousandths. So we would like to plane it down to the thickness of the part. So for this operation, we're going to use a method called 2-axis facing. So most methods in 2-axis requires you to select a part region, or also known as a control geometry for machining. In the case of facing, the system will automatically use the stock silhouette, which is the extent of the stock, to generate the toolpath. So you do not have to select a region or a geometry for facing. So it'll automatically use the extent of the stock to generate your toolpath. So I'm going to skip the selection of part regions in facing. We'll pick a tool for it. There are different tool types that you can select, and the system will automatically filter out the tools that you can use for this operation. So I'm going to use a face mill tool for facing operations. As you double click on the tool, you can edit the properties by specifying the tool diameter, the tool number. If you need to use a coolant, you can specify that, and also feeds and speeds can be determined here and established. So for this particular operation, we'll pick a face mill tool. The next step is to specify the feeds and speeds. The feeds and speeds are automatically loaded from the tool by default once the feeds and speeds are established in your tool. Next is the clearance plane. The clearance plane is your plane where all the transfer motion happens, or the non-cutting motions happens. And as the tab is active, you'll see that the clearance plane is displayed on your graphic screen. You can change the clearance plane. By default, it's set to automatic. If you'd like to change it to a much higher level elevation, you can use stock max plus a distance to alter or change the clearance plane. If you have any bolts or clamps in the way, if you want to change the clearance height, you could always do that using one of these options in here. Now, for our demonstration purposes today, we'll leave it as automatic. In the next step, we're going to specify the cutting parameters. The tolerance, since facing operation is considered like a roughing operation, the tolerance is set to a 10 thousandths, and the stock allowance or stock is set to 25 thousandths, which stock in 2-axis is an XY stock. So we'll set the stock to 0. This is in X and Y, and you can choose from the 2 different type of cut patterns. Typically, linear pattern is commonly used for facing out a rectangular block of material. So I'm going to pick linear. The angle of cut, I'll set it to 0, which means the cutter will traverse back and forth parallel to the x-axis. You can choose the cut direction to be climb, conventional, or mixed, and then specify your step over. And cut levels, I'm going to skip specifying any cut levels. We'll specify entry and exit in here for facing. I'm going to use linear and then generate. So I'm being prompted saying that no region selected. Would you like to use the stock silhouette to face? I'll pick yes. And the toolpath is generated, and the facing automatically uses the extent of the stock as your region. Now let's take a look at the Simulate tab. The Simulate tab offers you different controls to run the simulation. So as you look in the Simulate tab, you have these controls. Play will basically start the simulation of the cut material simulation. So when you select play, you have controls to pause your simulation. You can control the simulation speed as well as you go through the simulation. And selecting play again will resume the simulation. We have simulate by moves and simulate by distance. So if you want to run the simulation slowly, you can use simulate by moves, simulate by distance, and by toggling off simulate by moves. And you have additional controls under simulation preferences where you can further reduce the simulation speed. So we just did a facing operation to clear out the material that was being left on top of the part. And as you can see here, the system automatically used the stock extents, and the cutter goes past the stock extents here to clear out the material. So the facing treats the region what you select as the extent of the stock, and in this case, the stock silhouette is automatically used as the stock extents. Now, as you look at the toolpath and look at the toolpath displaying levels, you'll notice that the facing operation automatically determined the total depth as 2000 since it knows that the maximum part thickness based on the alignment of the part and the stock. So there was no need to select a region, and I didn't have to specify any additional parameters for the total cut depth. So it was automatically determined based on the part and the stock geometry. Now the next operation we're going to learn about here today is going to be pocketing. Now pocketing is an area clear operation. Now in this particular part, we have 2 blind pockets and we have 2 through pockets. Now to program these, we want to clear or hog all the material out inside these closed volumes. We're going to use a method called pocketing. That's under 2-axis. You'll find pocketing. Now since there aren't any drafts or sculpted bottoms, again this can be programmed using 2-axis pocketing operation. So for pocketing, you will need to select a closed region. We could do that by using select curve edge regions, surface boundary, or even flat areas. Today we'll be focusing on how we can use select curve edge regions. So we'll pick select curve edge regions. Now as you select curve edge regions, if you do not have any curves or sketches on the part, you can directly select face edges or surface edges from a solid surface geometry. Now, rather than having to pick each and every edge individually and having to select them, when you're working in Rhino, you can go to the Select tab, and there's an option to do what is called Select Chain. And then for the chain continuity, you can specify tangency, and all you do is pick one of these edges, and it auto chains it for you. Right-click to accept it. Now repeat the same step for the other pocket. Select Chain. We'll pick one of these edges and it auto chains it. Right click again to accept it. So right click or press enter when done, and this basically adds all of your part regions as your control geometry. The next step is to select the tool. We'll pick the 1/2 inch flat mill, specify feeds and speeds. So the feeds and speeds are automatically loaded from the tool. Now again, we have the clearance plane. So the clearance plane is the plane for transfers. So when you go from pocket 1 to pocket 2, you want to make sure that the tool is clearing your part and the stock material. So you want to make sure the clearance plane is set appropriately. By default, it's set to automatic, which will clear the stock or the part, whichever is higher. The cutting parameters allows you to specify the tolerances, the stock allowance. The stock allowance in pocketing is also an XY stock or a side or a wall stock. So if you specify a stock to leave, it's going to stay away from the side walls by the specified distance. Now, both facing and pocketing are considered as roughing operations, where you would like to typically want to leave some stock and then go back and finish them using like a profile operation. Now, if you'd like to finish it directly to the edge of the wall surfaces, you can set the stock to 0 and it's going to go finish right to the edge. You have different cut patterns that you can choose from in pocket operation. You have the offset cut pattern, offset spiral, linear, spiral, radial, and high speed. We'll pick offset. So selecting offset will create successive offset of the part region that you selected, the shape of the part region. You can specify your cut direction, your step over. Under cut levels, you could specify the location of the cut geometry. This refers to the location of the pocket boundary where you're selected. So we pick the pocket boundary at the top of the pocket. So we'll pick it, we'll set it at top. Had you selected the floor, you'd pick at bottom. So it's at the top. Now for the total depth, we can either enter the depth in here or you can use the pick control and you can pick the depth by selecting 2 points, one at the top edge, one near the floor. So the total depth is established. You could now cut this in multiple levels. We mentioned about 2.5 axis. So the total depth is a little over 550 thousandths, and we are splitting it into 2 levels automatically. So the first level will be at about 275 thousandths, and then the final level will be down at 550 thousandths. So the Z remains constant as the cutter traverses in X and Y in each of these levels. In the next step, you can specify the entry and exit parameters for pocketing. So how would you like to ramp into the pocket? You typically do not want to plunge in, so you can specify your options here for engage motions, retract motions. You can apply these for each of the levels and then select generate to create the toolpath. So if you toggle the visibility of the toolpath, you'll see the pocket toolpath has been generated. If I go to one of the side views, the front views, I can also display the toolpath in hidden areas. So you can see the toolpath through the shaded model. And you'll notice that the tool clears as it traverses from one region to the other. So that's your clearance plane. Now let's go ahead and run a simulation for the pocket operation. We'll switch to the Simulate tab. Now, we talked about how we can do a play to run the simulation. You can do a pause to stop it, and then play again to resume it. If you want to skip the simulation to the end, you can do a pause and then select Simulate to end. It's going to run through the simulation. Now, you also have an option where you can step the simulation in levels. If you select Simulate by Moves and click on Step in Levels, you can see it automatically simulates to end for each of the cut levels. Step levels again, it goes to the final depth. Step levels for the next pocket, step goes to the final. So you can use step levels when using Simulate by Move, so you can step each level of the simulation. Now that we have programmed the blind pocket, we would like to go back and program the through holes using pocketing operation again. So rather than having to create the operation by selecting the 2-axis methods and pocketing, you could make a copy of your existing operation. Right-click copy, right-click and paste. So it creates the copy of the operation. You can edit the operation by double-clicking on the folder. Remove your current selections by selecting Remove All. Use Select Curve Edge Regions. You can either use Select Chain to select them, or you could individually select each of those face edges. Right-click. Again, we are using the same tool, the same parameters. All I'm changing here is the total depth. We'll repick the depth. And then you can adjust your depth per cut parameters. If you want to take it out in 2 or more passes, you can specify your depth per cut. generate. Again, you'll notice that the clearance plane is set high enough so it clears the part material as you transfer from one cut region to the next. So if I run it using simulate by moves, you'll notice that the simulation goes at a much faster rate. So we now program the facing, the pocketing operation. The next operation I'm going to program here is to engrave the part number that's created in here. Now you can create these as curves using the text command in Rhino. We also have a single line font or a single stroke font that you can use to create the text. So to scribe or engrave the part number into the part, we're going to use a method called toAxis in engraving. Now the engraving operation will place the cutter right on the geometry. It's called like an on condition where the tool tip stays on the curves that you're engraving. So again, we'll use select curve edge regions, and we can pick each of these curves individually, or we can use the select tab, use select by color, and just pick one of these curves, and it'll automatically select all the curves that are of the same color. So once you have made your selections, right click or press enter to accept the selections for part region. We'll pick a tool for engraving. So I'm going to use a V-mill or like an engraver tool. In this case, it has a 45-degree taper angle. We'll set the feeds and speeds to be loaded from the tool. Again, clearance plane is set to automatic. The cutting parameters will specify a depth, and I'm going to set the depth to be 20 thousandths. We'll cut it in one pass, so the total depth will be cut in one pass of 20 thousandths. And for the entry and exit on the engraving, I'm going to leave it as none. So the cutter will just do a vertical plunge in the Z to engrave these letters. So we'll click generate. So the engraving toolpath is now generated. And since I've displayed the toolpath in hidden areas, you're able to see the, the toolpath as it's cutting beneath the top surface or the top face of the part. So you can toggle the display for toolpath in hidden areas. So let's go to the simulate tab. We'll pick play to run the simulation. So you'll notice that as it's simulating, it's cutting in a random order. So the sequence is basically the order in which you selected them. Now you can change that by going back to the sorting tab, and you can sort them to go in a minimum distance sort, starting from lower left corner. So it resequences it based on minimum distance to make it more efficient, your transfer between one geometry to the other. So now that we have programmed the facing, pocketing, and the engraving operation, now the last step left here is to relieve the part from the stock. And for this, we're going to be using an operation called profiling. And the profiling will be used to keep the cutter either to the right side or left side, which could be outside or inside for the part that you're trying to profile. So we'll do that by going to toAxis methods and profiling. For profiling, you could be selecting open or closed curves. You can profile for the control geometry or the part region. You can select curve edge regions or surface boundary or even flat areas. So for this example, we'll again pick curve edge regions. Since I do not have any sketches that are created on the part, I'll be using the face edges. Again, I'm going to use a select chain, and then I'll just pick one of these edges, and it auto chains everything that's coplanar. So right click to accept the chain, right click to accept the selections. We have all the curve regions selected, and these are highlighted on the part. We'll pick the same 1/2 inch end mill which we use for the pocketing operation. The feeds and speeds are set. Load from tool. Clearance is set to automatic. In the cutting parameters, you'll notice that the profiling operation is considered as a finishing operation. So by default, the tolerance is set to 1,000. The stock to leave is set to 0, which means it's going to finish it right to the edge of the part region that you've selected. You could pick your cutting direction. You could pick climb. conventional or mixed. Selecting mixed will alternate between climb and conventional as you cut between levels. You could choose your cut start side. You could pick outside or inside. So we'll pick outside in here. So we want to keep the cutter to the outside of this profile. In the cut levels, we'll specify the depth. Again, the geometry, what you selected for the profile is at the top of the part. So we'll leave it as at top. Cut depth, we'll just pick 2 points. You could pick any 2 points in Z. And the total depth is established. We could now break this up into multiple passes. I could say I want to break it up into 3 passes. I can just say divided by 3. That gives me 3 passes in here. Entry and exit. You could set the type of entry and exit. Apply these for each level. Generate. We have our profiling toolpath generated. And as you can see, it's automatically compensating for the tool and cutting on the outside of the part. We'll switch to Simulate tab and click Play to run the simulation. And anytime you can control the simulation speed. And as you notice here in the simulation, I've chose Remove Remnants during simulation, so it automatically removes the stock, the remnants from the stock once the simulation is completed. Now, once the toolpaths have been generated, we could go back and take a look at the workflow. Right-click Information will give you the estimated time for each and every operation that's been programmed in here. You can see we have 3 tool changes, going from a face mill to a flat mill to a V mill back to a flat mill. And you can always rearrange the operations if you need to before you need to post. So I can move the engraving after the facing operation, so we minimize the tool changes. We could also generate what is called a shop documentation in here. This will create a setup sheet, so right click and select shop documentation. And you can pick a template for the shop documentation here. I'll pick template 2, choose the location where you would like to save it, and pick save. And it automatically takes the screen capture of the active view for the setup sheet in your shop documentation. Once the shop documentation is generated, it automatically displays in your web browser, the default web browser of your choice. And there's your shop documentation with preview of each and every toolpath that you generated. Has information about the tools used, the feeds and speeds, the machining operations, the total number of tools being used, and the time. Now finally, we want to do a post process. We'll click Setup 1, right click, and Post. Specify a name for it. And there's the posted output file. Since we specified the work 0 to be 54, G54 is being output in your posted code. Now, folks, what we did right now here in RhinoCAM, we're going to quickly go over the same thing in VisualCADCAM to see, just to kind of give you a review of the workflow, how it works. So I'm going to switch from RhinoCAM into VisualCADCAM. I have the exact same part loaded in here. So the first step is we wanted to go ahead and orient the part. So we can use the CAD tools that are available to us in VisualCAD. We can do a Control-A to select all the geometries. And then you can either go to the Transform tab to use the Rotate command, or you can use the graphical manipulator, which is similar to what's called a gumball in Rhino. So we can rotate it, rotate the part, or we could use Setup, Orient Part in VisualCAM. We'll specify the spin angle, rotate it, click OK. Now the part is rotated. So in VisualCADCAM, you'll notice that there's 2 triads. The world coordinate system is marked with X, Y, Z labels on the triad, and the machine coordinate system is displayed slightly larger, and it appears right on top of the world coordinate system. So the next step is we wanted to move the part closer to the origin. So we use Align Set World Coordinates, set to part, lowest Z southwest. So the part is lined up towards the origin. We're going to define the machine tool, number of axes to 3. Select the post processor. We'll click FANUC. Specify the posted file extension. And then we are now ready to define our stock material. So we'll click box stock. Specify the stock dimensions. Stock height. Display the stock visibility. In the next step, we're going to align the stock to the part using align stock. We're going to align the Z to the bottom. So the bottom of the stock is flushed with the bottom of the part. And the XY, we're going to leave it as center, just like what we did in the previous example. And then we're going to establish the origin. We'll use align, set world coordinates, set the stock, lower Z, southwest. Sorry, we'll pick higher Z, southwest. So we want to put the Z0 to the top face of the stock in the southwest corner. So in the next step, we're going to start programming our toolpaths. So if you need to create a works area to establish a work offset number, we'll just choose G54, leaving the origin at the same location. Next, we'll do a facing operation, 2-axis facing. We'll skip selection of part regions. We'll select the tool, set feeds and speeds to be loaded from the tool. We'll set the clearance to be at automatic. We'll establish the cutting parameters. We'll pick linear cut pattern. Specify the step over. Again, we're not inputting any parameters for cut levels. We're just setting the entry and exit parameters. Generate. So the system automatically uses this silhouette extents of the stock. We'll switch to simulate tab. We have the stock defined. We'll click play to run the cut material simulation. Now once we're through with the facing operation, we'll program the pocket operation, 2-axis pocketing. To program these blind pockets, we'll use select curve edge region. Now, VisualCADCAM will automatically chain when you select a face edge by holding down the shift key. It auto chains the edges that are coplanar. So automatically it chains them holding the shift key when you pick an edge. So you don't have to click to select each and every edges. Select your tool for pocketing. Specify feeds and speeds. Clearance. Your cutting parameters, very similar to what we did in our example. Specify your cut pattern, your cut direction, step over, cut levels. We'll pick the depth. We'll step it in 2 levels. Specify entry and exit. Generate. So it clears the tool clears the material as it goes from one pocket to the next. We'll run a simulation. And you have the same controls where you can pause, resume, pause, simulate to end. You can also step through levels in the simulation. We'll repeat the same pocketing operation for the through pocket by doing a copy paste. Edit the operation, remove all, use select curve edge regions. Selecting by holding the shift key, so it auto chains it. The only parameter we'll be changing is the total depth. I'll break this up into 3 passes. We can do multiple passes. Double click to edit and regenerate. So you have all the controls in the simulation to control the simulation speed. So the next operation we'll do is the engraving. 2-axis engraving. Remove any of the pre-selected regions. We'll use select curve edge regions. Like how we did in Rhino, you also have the option to do select by color to automatically select all of these curves that you created, or the text you create for engraving. Right click to accept your selections. Pick a tool for engraving. Set your feeds and speeds, your clearance plane to automatic, and then the cutting parameters where we specify the total depth, generate. The toolpath for engraving is now generated. We'll pick play. We'll go back and slow down to rerun the simulation. Again, if you want to sort the sequence, you can always edit the engraving operation, specify a sorting sequence, and generate it. Now finally, we're going to add a profiling operation, 2-axis profiling. We'll remove the currently selected regions. Select curve edge region, holding the shift key. I'll just pick an edge, so it auto chains it. We'll pick the 1/2 inch end mill. We'll set the feeds and speeds to be loaded from the tool. Clearance to automatic. Cutting parameters, we set the start to leave as 0. We'll pick the cut direction to climb. Cut start side, we want to cut the profile on the outside. Cut levels, we'll pick the total depth. And we'll break it up into multiple passes. Specify entry and exit, generate. So it's profiling it in 3 steps, 3 levels. So as you notice, the cutter moves in X and Y, the Z remains constant, steps down to the next level, and repeats itself for the final pass. So we've now generated the toolpaths. You can take a look at the time estimates, right-click information. If you need to reorder the operation, you can reorder it. Right-click, shop documentation is also available in VisualCADCAM. Right-click and shop documentation. You can select the location where you want to save this to. Click save. Once the shop document is generated, it'll automatically appear in your HTML viewer. And then finally, we want to go back and post-process these toolpaths. Setup 1, right-click and post. And there's our posted code.